In addition to the regular regression formulation that we showed, the general formulation with z's, we can have different functions in nonlinear as well, and these will be not written, cannot be written in the general least squares form. For example, this function. In this scenario, we need to use an iterative solution to solve these cases, and Gauss-Newton method is an option for this. And Taylor series expansion is used to express the original nonlinear equation in an approximate linear form. So we linearize this function using Taylor series expansion. Then we use the least squares again to obtain new estimates of the parameters that move in the direction of minimizing the sum of squares of the residuals. So what we need to do is, first of all, in general, we write the relationship between the nonlinear equation and the data as follows. So this is the coefficients, and this is the data, and these are the outputs. Basically, a function of input gives output with the error as well. You can just simplify this as this one. Then this is expanded in a Taylor series around the parameter values and curtailed after the first derivative, or cut after the first derivative. For example, for a two-parameter case, we have the Newton-Raphson function. You can see here the first term, the first derivative term for a0, as well as first derivative term for a1. So this is only for two parameter, a second order polynomial case, or actually not second order, this polynomial. This is just one a1 exists here and a0. We cut after this point. In here, delta a0 and delta a1 are the current and previous iteration values. Because these are unknowns, we will solve for these. And substituting this into the previous equation gives this result. So basically, we will substitute it to here, y minus fx. Put it here, actually. Here, we can say y minus fx is the error. So we need to find the errors. That's why y minus fx is equivalent to fx is this. So we just put it here. Then it becomes this result, as you can see. Now we have this Newton-Raphson approximation of this function. And in this, we can put it into a matrix form. These, z delta a and e's, as you can see here. The z's are the derivatives. The derivative with respect to the first coefficient and second coefficient for two parameter case. And these, d values are y minus f values. You can see here, these are the actual data results. And we will also have the unknowns, delta a, in terms of delta a. And we will apply linear least square theory for this by using the same z-based formulation you can see here. For the solution approach, we solve first for this equation for delta a. Simply we take the inverse of this, put it here, and multiply by this. Then use delta a to compute improved results for the parameters. Then use these to have, so we will have initial a0 and a1. Add these values that you solve from here and find the next iteration values. Then use these again in here for these and these actually. Then solve it again and repeat the steps until convergence. Obtain the results after this. And you can use this approximation error between the unknown coefficients to be able to stop the iterations. We have an example here for using the Gauss-Newton method in an iterative base for this example. And the data is here, you can see. So we will start with initial guesses of 1 and 1 for the parameters. And you should note that these guesses, for these guesses, the initial sum of the squares of the residuals is 0.0248. Basically, you can calculate this. So partial derivatives, we need to calculate them first. And we know the function, so take the derivative of them. You can see here. Then obtain z for two coefficients, basically. and this 1 to n are the data, number of data, and put the first coefficient, the derivative with respect to first coefficient into first column and the second one into second column. In iteration 0, we will solve this, and we have the initial values of these, and z values will be these values. So basically use these initial values into these derivatives, a1 and a0 here, and obtain these results. Also use the data for the first row, for example, use these. For the second row, use this, and we obtain this z values. And if you multiply the transpose and regular z, you will obtain this matrix. And the inverse of this is this. So this is this matrix actually. And inverse is this value. You can calculate the inverse as well. And then d values. D values are the, if you remember, subtraction of fx1 from y1. y1, yn are these y values, but these f values will be the calculation using a0 and a1. If these are with this function, calculate these using the function actually. And when you use the function with a0 is 1 and a1 is 1, the function is like this. Put x1s, calculate y's, put them here, then subtract them like this. The result is this. Then use this to solve this equation. So basically we calculated these and also z's and multiply them. Z times d basically gives this result. And when you multiply this and this, you basically get delta a's. So we inverse this here like this, multiply it by this value, then obtain the delta a's, these values. So these are the updated a0 and a1 basically. So we started with 1, 1. Now it's minus 0.27 and minus 0.5. Then we continue in a second iteration, but for that we add the initial a0, a1 and the delta a's, and we obtain the final a0 and a1 actually here. Then the improved estimates of parameters are these values. Now we can use these new parameters in the sum of squares of the residuals, and you can calculate this value. Then you can calculate the approximation error between the initials and these updated ones. The results are 37, 33. You can continue to do computation until these values fall below the prescribed stopping criterion. We can say, for example, 1% or 10%, doesn't matter for now. The final result is 0.79 for A0 and 1.67 for A1. You can see that actually even with the first iteration, we reached these results almost, and we will continue a little bit more and we will obtain these. You can practice this at home or in your free time to solve and see how it goes. And these coefficients give us some of the squares of the residuals of, as you can see, the residuals are decreasing, so it's minimizing the least squares actually.